Okay, seems that we are live now. So we are ready to start one more lecture of our PNS on heterogeneous systems. And today we are going to cover another important parallel pattern that is called prefix sum or scan. It's probably my favorite parallel pattern. Before we start talking about the prefix sum or scan, let me quickly remind you the other parallel patterns that we have already covered in the course. The first one was the reduction. Remember that a reduction is an operation that reduces a set of values into a single value. This needs to be an associative, commutative operation and also have an identity value. That's the case of the sum, product, minimum, or maximum. And reduction is a key primitive for parallel computing. Same as scan is also a key primitive for parallel computing. Remember that when we were discussing the way to implement reduction efficiently on a GPU, we talk about the idea of mapping threads to the operands and to the operations in a divergence-free manner, such that when threads start to retire, because after each iteration, remember that in the tree-based reduction, half of the threads retire. The threads that keep working belong all to the same warps. And this way, we will be able to maximize the warp utilization. The second important parallel pattern that we studied was the histogram. A histogram, as you may remember, is an array where we have a set of elements that are called bins, and these bins are essentially counters. So the goal of the histogram is to count the number of occurrences of certain values or of every value in the input of the histogram calculation. What we essentially do when calculating a histogram is reading elements from the input, checking what's their value, and depending on their value, we will update the corresponding bin, the corresponding counter in the histogram. Remember as well that we can create histograms in parallel in order to make it faster, but when we have threads executing concurrently, we have to be careful because sometimes these threads will need to update and access the same memory locations. And if we want to avoid data races, we will have to use atomic operations. Atomic operations have the problem that they serialize the execution, especially when there are conflicts in the access to the histogram. And we were discussing ways of optimizing these. And the most commonly used optimization technique here is the privatization. In the privatization, what we do is calculating subhistograms. These subhistograms can reside in shared memory of the GPU cores. And after each thread block has computed its own subhistogram, we can perform a parallel reduction and obtain a final histogram that will be stored in global memory. The next parallel pattern that we discussed and we presented it in the last lecture is the convolution. Remember, convolution is a widely used operation in different fields like signal processing, image processing, video processing, and so on. And convolution consists of applying a filter, or also called mask, on every element of the input. For example, if it's an image, we will apply this filter on every pixel of the image. And what we obtain as the output value for every pixel, for every position of the image, is a weighted sum of the set of neighboring input elements or neighboring pixels in the case of image processing. We were talking and discussing different applications of convolution, and probably the most important one these days is the application to machine learning and artificial intelligence in the form of convolutional neural networks. We talk about the convolution and how to optimize it. Remember that in the convolution, we apply the mask over all the elements of the input image, or the input array. We obtain a series. We obtain some partial products, and then we can reduce these partial products to obtain the final value for the output array. And that was a 1D convolution, and here we have a 2D convolution. That's actually, this example corresponds to a CNN, a convolutional neural network or a convolutional layer. In this case, we are applying a 2-dimensional filter on each pixel of the image or the input feature map, obtain the partial products, reduce them, and obtain the final value. And we also discussed about how convolutions are used in machine learning and how they can be converted or lowered into matrix multiplication in order to make them even more suitable for the GPUs. This is the slide where we explain how to go from the convolutional shape to the matrix multiplication shape. I don't know if there are any questions about the previous parallel patterns. If not, I think we can continue with the parallel pattern that we are going to cover today, the prefix sum or scan operation. So let's start with the definition. A prefix sum or scan operation is an operation that takes an input array and an associative operator, same as we have seen in the reduction. And associative examples of associative operators are addition, multiplication, minimum, and maximum. And by using this input array and the associative operator, the scan or prefix sum operation will return an output array that is the result of recursively applying the associative operator on the elements of the input array. If you want to see it more formally, let's start considering an array of n elements from x0 to xn minus 1. And the associative operator, whatever this is, for example, the addition operator, and we will obtain an output array with elements yi, where each element yi is the result of applying the associative operator on all the previous elements of the input array. Observe that we have here what we call the exclusive scan. In the exclusive scan, the element I of the array, the output array Y, is obtained by applying the associative operator from element 0 to element I minus 1 of the input array X. And this is why we call it exclusive, right? Because we are not considering element Xi. We are only considering until element xi minus 1. If we consider element xi as well, then we are talking about an inclusive scan that goes or applies the associative operator to all the elements from x0 to xi to obtain yi. A scan, as I said in the beginning, is very widely used. It's a key parallel primitive that has very interesting properties. And one key property is that it can convert recurrences from sequential. This is a sequential code where we apply certain function on the index I, and then we, in this case, are adding, this could be a different associative operator, to the previous element of the output to obtain the corresponding element of the output I in this case, and we can convert this into a parallel execution, because we can calculate all these fi for each I element of a certain input array, for example. We can calculate all of these in parallel, and after that we can perform an scan operation. And this is what we do in many parallel algorithms that use scan as a basic building block. And here you have a few of them, such as string compaction, partition, select, unique, sorting algorithms, string comparison, and so on. At the end of the lecture, we are going to talk about some of these examples in a little bit of detail. But yeah, let's first start about talking about the operation itself and how to implement this prefix sum or scan operation efficiently on a parallel processor, and in particular on a GPU. Here we have a simple example. This is our input array. This is the way that we are going to calculate the output when we perform an exclusive scan. Observe that this is just a sequential code. The first thing to do here, by the way, we are assuming not only in this slide, but also over the course of the presentation, that the associative operator is going to be an addition. Whatever we explain for the addition will be equally applicable to any other associative operator. So as I said, we are going to start initializing the first element of the output, out0, with the identity value, which in the case of the addition, as you know, is 0. And then we go over the rest of elements of the input and the output and compute each output I from the output for the previous position plus the value in I-1. So the value in the input array for the previous position I-1. And this is what we obtain. Observe that the first element in the output is 0. The second element in the output is the result of adding 0 plus this first element in the input array, that's 1. The next element here is the result of adding these two elements, x0 and x1, or what is the same, this out 1 plus this in 2, right? So this is actually in 1. So this is out 2. Out 2 is equal to out 1 plus in 1. That's the way that we calculate all the elements of the output array in the case of exclusive scan. And in the case of the inclusive scan, remember, we consider the element itself of the input in this case. So we consider the element in I, and we obtain this output array. So in this case, we initialize the first element out0 with the value of in0 of the input array. So we directly write this one in the output element, and then we compute this next element, which is out1, as the result of adding this out0 plus adding this in1. And this way we obtain all the elements of the output array. So as you can see, both are essentially very similar. In the end, most of the elements are common, and so most of the results are common. Is just essentially the difference between the output of the exclusive scan and the output of the inclusive scan is that one is shifted with respect to the other one, right? So that's why we are going to focus only on one of them. We are going to focus today in the inclusive scan. So we are going to start discussing about how we can implement this on a GPU. And the way to implement this on a GPU is by applying what we call the hierarchical or segmented scan. We need to do it this way because this input array might have millions of elements, as you can imagine. And when we have so many elements, we cannot have we cannot have a single thread block operating on all the elements at the same time. So what we will do is partitioning the input array in equally sized chunks that are assigned to the different thread blocks that are going to run on the GPU cores of our GPU. And in the first step, we are going to apply a local scan. So, or we are going to apply the scanning segments, and each of these segments is the chunk of the input array that we have assigned to each of the different blocks. This is assigned to block 0, this has been assigned to block 1, and so on. And each of the thread blocks is going to compute the partial scan on the chunk that has been assigned to it. So for example, this is an inclusive scan, and in this array of partial results, what we see is that these 4 elements are obtained by applying the inclusive scan on these 4 elements here. And if we check the elements that block 1 will calculate, here we have applied the inclusive scan on these 4 ones, as you see. So 1, 1, these 2 is the result of adding these 2 ones, these 3 is the result of adding these 3 ones, and so on. And it's exactly the same for the rest of blocks as well. But now, how do we go from this array of partial scan operation or per block scan results to this output that is the actual inclusive scan for the whole array? Well, there are some observations that we can make here. For example, if we check this 14 that corresponds to the last element of the second chunk, the chunk that was assigned to block 1, we see that this 14 is the result of adding these 4 and this 10. And if we think about this 20, we will see that this 20 is the result of adding 6 plus 4 plus 10. So in the end, what we are doing here for every element of a chunk is propagating the reduction results of the previous chunks. Because if you think about it, you will see that this 10 here is actually the reduction result, the sum of all these 4 elements. This 4 here is the sum of all these 4 elements. And by adding 10 plus 4, which is 14, and then adding this 14 to 6, we will obtain this 20 in the output array. So what this essentially means is that we are taking, or we have to take, the last element of each of the per block scan operations and then apply a scan of partial sums to these reduction results, to these last elements of each of the per block scans. So in some way, we will move these values 10, 4, 6, and 8 to another array, and then we apply this a scan operation on this array of partial sums that is much shorter. As you can see, in this case, it only has 4 elements instead of the 16 original elements that we had. So now we take again the array that we generated before in the first step, this array of per block inclusive scan, and we add the corresponding elements as if they were an offset to all the elements of each of the chunks. So here, these 4 elements, we add 10 and we obtain the final result. Here we add 14 and we obtain the corresponding final result. And here we add 20 and obtain the corresponding final results, right? Is that clear? Are there any questions so far? Okay, yeah, but now there is something that happens here. If you think about how this whole process is going to be executed. At the very beginning, in this first stage, we are partitioning the input array into equally sized chunks and assigning each of them to the individual thread blocks. And then we start running the thread blocks on the GPU cores, right? But now remember that the number of GPU cores that we have inside a GPU is limited. It might be 100, it might be 26, it might be 128, whatever, but it's a limited number. But the number of thread blocks that we can create when we launch our program, remember the concept of the execution configuration. When we launch a kernel, we decide what's the number of thread blocks that we want to launch and what's the size of these thread blocks. The number of thread blocks might be much, much larger than the total number of GPU cores that we have in our GPU, right? So what this means is that the thread blocks are going to be scheduled as there is some free space on the GPU cores to execute them, right? And so it might take a while for all the thread blocks to get executed on the available cores. So what that means is also that we don't know exactly when all these elements of this array of per block partial scans, when all these elements are computed. It might turn out that this block 0, for example, starts executing at the very beginning, but maybe this block 3 or maybe block 1 million executes many microseconds or milliseconds later. So in the end, we need a way to make sure that all thread blocks have finished before we write all these last elements of each block or these reduction results into an array and start performing this scan operation of partial sums. And the only way that we can to do that is to use some way of interblock synchronization. And this is something that we already talked about when we presented the parallel reduction, and here is more or less the same. We need to perform a interblock synchronization in a bulk synchronous parallel programming model, as it's the way that we program GPUs, the CUDA programming model, for example. What we typically do is terminating a kernel and starting a new kernel. So in the particular case of the scan, after the first kernel where we calculate the per block scan operation, we will have to terminate the kernel and then start maybe a new kernel for the scan of partial sums, or calculating this scan of partial sums on the CPU. That will depend on how large this small array is. If it's only 4 elements, for sure you don't need a GPU for that. You can do the scan operation on CPU. In the end, the input array might have millions of elements, so probably this array of partial sums will be as well quite long. So we might prefer to launch a new scan kernel to perform this scan operation. So there is some recursiveness as well, as you see here. And we also talked during the lecture of the reduction that another way of doing this interblock synchronization could be using arithmetic operations in global memory. And today we're also going to use a similar idea here, using atomic operations in global memory to perform this synchronization in some way. But this is something that we will cover and we will discuss at the very end of the lecture. The thing is that after this second step, let's, for example, imagine that we do this on the CPU or on the GPU, launching a new kernel, we will have to synchronize again, which means terminating the previous kernel and starting a new kernel. And now we read again this array of partial per block scan operations that we had stored in global memory. So now we read it again from global memory, and now we add the offsets that we calculated with this kind of partial sums, as we have just seen. So now let's start with the first step here, right? So we need to learn the way of implementing the per block scan. So let's now focus on a single block. By the way, inside a thread block, we can also apply the hierarchical approach. And because remember, we have a hierarchy of a software hierarchy, and this software hierarchy has the grid of maybe millions of threads, and these are grouped into thread blocks, but these thread blocks are later decomposed into warps, and warps are composed by 32 threads, right? So in the end, the same thing that we are doing, or we did in the previous slide, dividing the whole scan operation into a hierarchy, into different steps. Here we can also apply inside the same thread block, we can also apply kind of a hierarchy, but that's not the first thing to talk about. Before that, we are going to start talking about the basic algorithms to implement a per block scan operation. And there are two basic algorithms. There are more actually, but two important ones that we are going to introduce in today's lecture are Kogi and Brent-Kohn. So let's start with the first one, with the Kogi parallel inclusive scan that you can see in this slide. So we start with an input array. In this case, our input array is very short, as you see, is only 8 elements. And the way to go is to assign, as we normally do, assign one thread per element of the input array. So now these threads start executing the scan operation. So they start doing executing additions. This thread here will read element x0 and its own element x1, and we'll add them and store them in memory. This thread here will read element x1 and will read element x2 and add them and store them here, and so on. That will be, this is the first iteration. Then we go to the second iteration. Now observe that thread 0 and thread 1 are retired, but thread 2 continues the execution in this next iteration. So this thread 2 takes element x0 and adds it to the value that it computed in the previous iteration. So now we obtain x0 plus x1 plus x2. And it's the same for the rest of elements, as you can see. Now there are 4 threads that are retired, and only 4 threads continue the execution in the next iteration. So now, for example, this thread here, which is thread 4, is reading the value that it computed in the previous iteration, and it's reading element x0 as well. And this way we obtain the final result, x0 plus x1 plus x2 plus x3 plus x4, right? And this is the result of the inclusive scan for this element of the output array. So as you can see, the process is relatively simple. I mean, the algorithm is relatively simple to understand. Observe also that it's an iterative algorithm, and in particular, it has, in this example, it has 3 iterations, and we have 3 iterations because we have 8 input elements, right? So what this means is that for an array of size n, the number of iterations will be log n. And this is how the code looks. Here you have on the right-hand side, you have the Kogi stone. I mean, you have the figure from the previous slide in order to connect easily the figure to the code. Observe that first of all, what we obtain is an index that relates to the block index and the thread index as usual. First thing to do is to moving the input value to the output value, to the output array, because we are going to operate on this output array. And in order to do so, or after doing so, we will synchronize to make sure that all warps have already performed, are already done with this copy. And then we start with this for loop. Now observe that the for loop has an index that is called stride, and this stride tell us what's the distance between the element that we for each thread have as its own element, the element that has been assigned to it. So, for example, output I for thread I, and we are adding the element that is at a distance stride. So when we start the execution in the first iteration, stride is equal 1. So that's why thread 1 adds element x1 and element x0, and thread 2 adds element x2 and element x1, right? That's what we see here. If we if a stride is equal to 1, we are reading the element I minus 1. We are storing it into this variable here, and then we add this element to the own element output I. Observe also, this is important, that we need to synchronize. Why do we need to synchronize? Because we are using multiple warps here, and these warps get scheduled and executed at different times. The first place where we need to synchronize is here to make sure that all threads have read the corresponding element of output, because in the end we are going to overwrite whatever is stored in the output I elements, right? So that's why we need to synchronize to make sure that all threads of the block have already accessed the value that they need to read, so have read this value before overwriting some other value in the output array. And then we finally synchronize again, and then we restart. We go to the next iteration. In this case, a stride will be equal to. So as we see in the second iteration here of the figure, we are also taking elements from that are at distance 2. And in the last iteration, iteration 2 in this case, for the array of 8 elements, we are reading elements that are at distance 4. Okay, let me know if there are any questions. Okay, so now one last clarification here is that we didn't make any assumptions here about where these input and output are stored, but in principle, if we don't make any assumption, we have to assume that they are in global memory. So these input and output are arrays, input and output arrays in global memory. But the interesting thing is that in the end, we are reusing all the time the same values, right? So there is a lot of data reuse, and what this means in GPUs is that we can take advantage of on-chip memory spaces, for example, the shared memory, right? So what we do is that instead of operating on the output array directly, as we saw in the previous code, operating on the output array directly that resides in global memory, and remember that the accesses to global memory are pretty slow, we are going to store these chunks of the output array into the shared memory, and this way the accesses to the to all these partial values until we obtain the final inclusive scan are much faster, right? Because the array resides in the shared memory. And that's essentially what we do in this code. If you compare this code to the code in the to the previous code that we discussed, you will see that they are exactly the same. The only difference is that instead of writing and operating directly on the output array, this output array here, we are operating on another array or on a buffer, in this case, buffer S, that is in shared memory. As you can see in this initial line, we operate all the time on buffer S, and only when we are completely done with this kernel that calculates the per block scan operation, we write to the corresponding element of the output array. By the way, you will also you also identify this if statement at the almost the very end of the kernel. This if statement is only, or the body of this if statement is only executed by one thread in the whole thread block, and in particular the last thread of the thread block. So in this we are using a thread block of block dim size. So this thread ID x equal thread ID x.x equal block dim -1 is the last thread of the thread block. So this guy here is storing its own result into some array of partial sums that resides in global memory. And this array of partial sums is the short array that we are scanning, that where we perform the prefix sum of partial sums that we have previously discussed in the second step of the hierarchical inclusive scan. So one more observation here is that we are using two sync threads. And the reason why we are using two sync threads here is because we don't want to overwrite values that are stored in the buffer S and are needed to compute the new values in the next iteration. So that's why we are using two sync threads. But you know that sync threads are costly, essentially because warps executing and finding a sync thread will have to wait until all other warps belonging to the same thread block reach to that point. So in the end, we are wasting execution cycles. We should try to avoid these sync threads as much as possible. And one way of doing it is by using double buffering. So instead of using a single buffer S, we are going to use two. So we will start with our input elements stored in some buffer 1 in shared memory, and we start executing the iterations. In the first iteration, the input is in buffer 1, and the output is going to be stored into another buffer 2 in shared memory as well. We will have some threads that don't work. In the first iteration is only thread 0 that doesn't really perform any addition, any computation, but we need this thread 0 to copy the corresponding element x0 to the output buffer, buffer 2. And then we go to the next iteration where the input buffer is buffer 2 and the output buffer is buffer 1, and so on. Right? So this technique is called double buffering, and in this particular example of the per block scan operation allows us to get rid of the sync threads called the barrier that we had here, right? That we had here after, so when reading the input element. So in the end, we will be able to probably execute this faster because we are removing one sync thread, so we won't have so many wasted cycles due to some warps waiting for others, right? There is this might be kind of a double-edged sword, right? Because the fact that we are using more shared memory as well might cause a reduction in the occupancy. Remember the lecture where we covered the performance considerations and we talk about the occupancy of the multiprocessors or the occupancy of the GPU cores, and we said that this occupancy was related to the usage of the resources, the hardware resources, such as registers or shared memory that the threads executing on each GPU core make, right? And if you are allocating now twice the amount of shared memory, it might happen that the actual occupancy gets reduced. And maybe because of that, we may have worse performance. But that's something that will depend a lot on the specific case. And by default, I would recommend to try and see what's the case. It might be that we have enough shared memory and we don't have this problem, or it might be that even by getting the occupancy reduced by a little bit, we still perform well, or even better in some cases than the original implementation, because, for example, we may have less contention when accessing memory. I mean, these are different things to try, and some of these optimizations are not always applicable, but for sure are definitely worth considering and trying. So this is, let's say, our most optimized code so far, the one that uses shared memory and uses double buffering. So this seems pretty good implementation, but we are going to analyze it a little bit more. We are going to see if it's work efficient. What does it mean? We say that one parallel algorithm is work efficient when it performs the same amount of work as the corresponding sequential algorithm. So let's think about what's the work efficiency of the scan operation or prefix sum. If we think about the sequential scan, we know that the total number of additions, that is, the total number of, or the amount of work that we need to perform to execute the sequential scan is only n additions for an array of n input elements, right? Because in the end, what we do is adding element 1 plus element 0, and then element 2 plus the result for element 1, and so on, right? So in the end, we are executing one addition per element in the input array. If we have n elements, we will execute n additions. But now, if we look at Kogi's tongue, we can see that we are executing many more additions, right? It's not 8. Only in this first iteration, it's 6. Sorry, it's 7, right? So if you then add the rest of iterations, you will see that it's many more than n, many more than 8 in the particular case of this toy example here. So actually, we have in total log n steps, as we discussed before. For an input array of 8 elements, log n is equal to 3, as we see in the string in the screen. And then in each operation, we perform n minus a step minus 2 to the step operations per step. So what that means, I mean, if we unroll these, what we will obtain is this sum here. By adding all these values, we will obtain this final number of additions that are needed to perform the Kogi's tongue parallel scan operation. And this is in the order of magnitude of n times log n operations. So the algorithm is not work efficient. Why is that? Because it needs more operations than the original sequential scan. So it's not work efficient. And the problem with that is that we may end up being very inefficient, or this parallel algorithm might end up being very inefficient in case we are limited in resources. And let me give you an example. You could implement this algorithm this way, right? This Kogi's tongue algorithm in this way, in a parallel manner, using multiple threads. But then it might turn out that your GPU is actually not such GPU. It doesn't really have so many processing elements to execute all these additions in parallel. Imagine that you want to execute this parallel implementation in a system that has a single processing element, a single core. So what that means is that we will have to first execute this addition, then this addition, then this addition, and so on, right? So if we execute this code on a CPU, what we will end up executing is all these many operations that are much more than the number of operations needed in the sequential version of a scan. And by the way, this is something that may happen in other programming languages. In this course, we are mostly focused on CUDA, but OpenCL is a very similar programming language that is cross-platform, and it also uses the bulk synchronous parallel programming model, very similar to CUDA, as I said, but it's cross-platform. And what that means is that whatever code we execute in we write in OpenCL, we can execute it on a GPU, or we can execute it on a CPU. So again, if you write this algorithm using OpenCL and then execute this algorithm on a CPU, probably it won't be very successful if you're using a single core of the CPU and not using, for example, SIMD extensions of the CPU, because you will end up executing many more operations than if you execute the sequential version. So because this algorithm is not, the Kogi-Stone algorithm is not work efficient, we are going to discuss another algorithm that is more work efficient, and this is Brent-Kong parallel inclusive scan. We start again from the same input array of 8 elements. Here we have some threads working, not all the threads as you see. We will only use one thread for every 2 elements. In the next iteration, half of the threads retire, so now we have only 2 threads performing additions, and then let's say this is the last iteration of this phase of the algorithm. We have a single thread computing this last element. So after these 3 steps, or these 3 iterations, we have already 4 values, the ones shaded in green, that are the final value that we will have in our output array. But we don't have all of them. There are still 4 more values to calculate, right? These are the white ones. So after this, what we call reduction step, we need a second phase. And in the second phase, we will have other threads computing the additions that are still missing. And after 2 cycles, or after 2 iterations in this case, we will be done with this post-reduction step. And this way we have the final output for the inclusive scan. Now let's analyze the work efficiency of this Brent-Kong parallel scan and compare it to Kogi-Stone. Recall that in Kogi-Stone we have log n steps, and the number of operations is in the order of magnitude of n times log n. So now if we think about Brent-Kong, we see that we have first a reduction step, and in the reduction step, this part here, there are log n steps, and we can count what's the number of operations in each iteration or in each step. And then we execute the post-reduction step, this part of the algorithm, where we have log n minus 1 steps, and we can also count what's the number of additions or the number of operations that we execute here. So in total, we have 2 times log n minus 1 steps, and the total number of operations is around 2 times m. And this is in the order of magnitude of n. So it's much closer to the sequential algorithm, to the work efficiency of the sequential algorithm, and it's also significantly better than the n times log n from Kogi-Stone. So even though Brent-Kong takes more steps, it's more work efficient. So in principle, it could be better, or at least, as I said before, if we were to execute these on a machine that has constrained resources and a sequential machine, for example, we should expect that it will be faster than the Kogi-Stone, right? But that's not always the case. And actually, there is a problem with Brent-Kong when executed on a parallel machine like a GPU, on a SIMD machine like a GPU. Remember that these threads that are executing these 4 additions are executing in lockstep. And these are not the only 4 threads that are executing. There are also inactive threads. The thread that is goes here, the thread that goes here, the thread that goes here. And on the other side, in Kogi-Stone, we are using all the threads. So actually, in this first iteration, we are also using for executing the additions all the threads except thread 0, right? So, but the problem with Brent-Kong is that if these 8 threads belong to the same warp, they execute in lockstep, right? And 4 of the threads are active and 4 of the threads are inactive. But we are not really saving additions, right? Because even the inactive threads are there. And even though they don't commit the result of their addition to the output register or to the output memory location, they are still consuming cycles. So the fact that we are only executing 4 additions here instead of 7 doesn't mean that we are executing this faster, because in the end, if you think about how a GPU schedules warps and how the warps go through the pipeline and execute, we will need essentially 1 cycle for these 4 operations and also 1 cycle for these 7 operations. So in the end, we cannot expect the performance of Brent-Kong being faster than the performance of Kogi Stone on GPUs. Still, it's a very interesting algorithm, an interesting case to study, and I would recommend you read more about it in the Programming Massively Parallel Processors book. But for now, we will keep working and we will keep focusing on Kogi Stone, even it's not so much work efficient, but in the end, it executes less iterations, and as a result, it will probably be faster on GPUs. So now let's go back to let's continue the implementation of the complete inclusive scan operation, and remember that we said that we could also apply a hierarchical approach to the inside each thread block, right? Because there is also a software hierarchy there with warps and threads. And when it comes to using warps, remember that there are some functions that appeared in the Kepler architecture, actually, of NVIDIA GPUs, that are the warp shuffle functions that allow us to communicate threads executing inside the same warp without having to use shared memory and having to use sync threads. They can directly read, each thread in a warp can directly read from the registers that have been assigned to other threads in the same warp. And we are going to take advantage of these warp shuffle instructions to implement this hierarchical approach to the per block inclusive scan. Remember that this was our hierarchical scan. Let's say the whole hierarchical scan, where we divide the input array into multiple chunks, assign 2 different blocks, and so on. Then we said, oh, after this first step where we calculate the per block scans, we need to synchronize. We calculate the scan of partial sums, and then we synchronize again, and finally we launch the last kernel where we perform the additions, right? We can apply exactly the same approach inside each thread block, but instead of dividing the whole thing into chunks that are assigned to blocks, we take the chunk that was assigned to a thread block, divide it into sub chunks, and assign each of them to different warps. In this case, let's assume that our thread block has 4 warps of 4 threads. But in the end, we will execute the algorithm in exactly the same way. First of all, we perform the per warp inclusive scan for warp 0, per warp inclusive scan for warp 1, and so on. We obtain these partial sums, these partial reduction values here. We scan them, and then we propagate the results of this scan of partial sum that represents kind of offset that are sent to each of the individual thread blocks to execute, to perform this final addition and obtain the result. Now, there is a key difference with respect to the this hierarchical inclusive scan, is that now we are working, all threads are working inside the same CUDA core, inside the same GPU core, and because of that, because they belong to the same block, they can use intra-block synchronization. They can use sync threads. We don't need to terminate kernel here or use atomic operations or something like that. We are only using a sync threads after this first step, where all warps calculate their per warp local scan. We use sync threads, then we perform the scan of partial sums, then we use sync threads again, and then we propagate these offsets that are later added to the partial per warp scan operations. So let's see how we can implement efficient per warp scan using warp shuffle operations, and that this is our warp scan function. We start defining the warp size. It's a constant equal 32, as you know, and we are also going to use this lane ID and warp ID that identify each thread inside the same warp and identify the warp inside the same block. So in the end, this expression here, thread ID modulo warp size, is obtaining the lane ID, that is the thread number inside a warp. So in warp 0, we have 32 lanes, from lane 0 to lane 31. In warp 1, that has thread IDs between 32 and 63, we also have 32 lanes, right? And these 32 lanes have a lane ID from 0 to 31 as well. But the warp size will be 1 instead of 0. So we are going to use these two indices. And then the warp scan operation itself that we define here as a device function takes one input value per thread or per lane, and then executes in this case, the Kogi stone implementation, but using shuffle operations instead of reading and writing from shared memory and synchronizing. So again, you could compare this for loop to the one that we have seen in the previous slides, in the previous codes, but in the end, we are doing exactly the same thing. Instead of calling it the stride here, we call it offset, but it starts, this index starts in 1 with this shuffle up sync instruction. What we do for each of the threads is to read the corresponding register X in the element, in the thread that is at a distance offset. For example, in the first iteration, when offset is equal 1, thread 1 that executes here read its own element, and also will use the value X from thread 0. And thread 2 will read its own element, but also will read the value stored in register X in thread 1, and so on. And then in the next iteration, now offset will be equal to, so now the distance between the threads from where we are reading a register is 2. Right, and this is the addition itself is only executed by the corresponding threads or the corresponding lanes in each iteration, and so on. And then we will finalize and return a value. In particular, by the way, this, as you can see here, because we are subtracting the input value, is this is an exclusive scan. But in the end, as you have seen, there is not much difference between inclusive and exclusive scan. So now let's see how we use this warp scan in order to implement our per block hierarchical scan. And this is the figure of our per block hierarchical scan. We start this block scan function, declaring some space, some shared memory space, this S data, and first thing is to execute the per warp inclusive scan. So all the threads in each warp call this warp scan function that we defined in the previous slide. And after executing this warp scan function, we will obtain this warp prefix. The last lane in the warp, lane ID equal warp size -1, will store the corresponding warp prefix into shared memory, right, in the corresponding position for this warp in particular. So in the end, what we are doing here is the last thread or the last lane of warp 0 is taking this value 10 and writing it into shared memory, into the S data array in shared memory. The last lane in warp 1 takes this 4 and writes it into the next position of the array S data in shared memory, and so on. Then we synchronize. This is this intra-block synchronization that you see in the figure. And then we only need a single warp to perform this scan of partial sums. And in this case, we are using warp 0, so all threads with a thread ID lower than 32. So those threads that belong to warp 0 execute the warp scan operation and store the result in S data. So then we synchronize again, corresponding to this synchronization point here, and then we can propagate the results of the partial, the scan of partial sums, and then perform the final addition. As we see, actually, no, it's actually here in this line. We are adding the previously calculated warp prefix that we calculated in the first step. We are adding it to the value that is the result from the scan of partial sums, right? Yeah, so in the end, here we may want to synchronize because probably the last thread of the thread block may add the corresponding value to some other counter where we are accumulating, in this particular case, accumulating all the reduction results for the whole block. But that's, let's say, not so important in this case. Important thing is that first we perform the per warp inclusive scan, then we scan this short array of partial sums that resides in shared memory, and finally we update the results from the original per warp scan. We update them with the scan values of the scan of partial sums, and obtain the final result. So this is what this is the code. This is how it works. The per block hierarchical scan. Yeah, guys, don't hesitate to ask if there are questions. Okay, yeah. So now we know how to implement a very efficient per block hierarchical scan using warp scan, using shuffle instructions, synchronizing using sync threads, but the least we can do, and in the end, writing a highly efficient per block hierarchical scan. But now let's go back to the let's say, complete hierarchical scan that assigns the input to multiple blocks and performs 3 steps. Remember that these 3 steps are first this per block inclusive scan, then we have the scan of partial sums, and then we have the add operations, right? So this is why we call this implementation scan add, because the first stage or the first kernel is scan, the second one is scan, and the last one is a add operation. It's a kernel that simply reads the elements from memory and adds it to each of the element one particular value that was previously obtained in kernel 2 in the scan of partial sums, and we update the values, right? And remember that we can we need to synchronize different blocks between stages, so we need to use this inter-block synchronization. You can see this as, and actually that's how it normally is. This is 3 different kernels. After the first kernel, we synchronize, so we terminate the kernel. Then we have a second kernel, we calculate the scan of partial sums, we synchronize again, and then we have the third kernel, the add kernel, right? So now we can analyze these, so how many accesses we have to global memory. In the end, remember that accessing global memory is probably the longest latency operation that we can execute inside a GPU. So, so yeah, and we will have to read and write several times from global memory. Why is that? Because after terminating the first kernel, here we terminate the kernel, we have to do this interblock synchronization, and when we have a kernel termination, the only way of keeping the results is to store them into global memory. We cannot count on keeping some values in shared memory for them to be used by a later kernel. No, that's not the way it works. You can assume that the shared memory is completely flashed. So if one kernel wants to use something that was computed by a previous kernel, it will have to go to global memory to read it. And that's why we need to analyze what's the number of global memory accesses in each of these 3 steps. In the first step, scan operation, the first kernel, we have to read the whole input array. This input array has n elements, right? And after reading the whole input array, we compute the per block inclusive scan, and we have to write the partial results or this partial scan again to global memory. Why is that? Because we will have to terminate the kernel, right? So in the end, in the first kernel, we are reading n elements and we are writing n elements to global memory. In the second scan, in the second operation, in the second kernel, sorry, the scan of partial sums, we are also reading our one array from global memory and writing it. But this array is much shorter. It's the size of this array is n divided by block size, by the number of elements in the chunk that was assigned to each block. So that's why we go from 16 to only 4 elements in our toy example. So in principle, we can consider that this is negligible compared to the n elements that we had to read and write in the first kernel. And then in the last kernel, in the third one, the add kernel, we again read n elements. Now we add these offsets to each of the n elements, and we also have to read those from global memory, but those are it's a much shorter array, as you know. And after reading this whole array of n elements, we have to add and then write again all elements to global memory. So in total, if we consider the size of the array of partial sums negligible, we will be reading and writing 4 n elements from global memory. And this is a lot, right? Let's see how we can optimize this. We can come up with another implementation for the hierarchical scan. And in this particular case, what we are going to do is the first kernel is only going to be a parallel reduction. We don't calculate the partial scan operation in the first step. And why is that? Because for the second step, in reality, we don't need the whole output, the whole per block scan. We only need the last element of that per block scan. We only need this reduction result for the chunk that was assigned to each thread block. So this 10 is the result, the reduction of 4 plus 3 plus 2 plus 1. This 4 is the reduction result of these 4 ones here, right? So in the end, we can, in this first step, just execute a reduction instead of the per block scan operations. The reduction, as you can imagine, is going to be faster because, or we should expect it to be faster because we are not executing so many operations. And then in the second step, as we did before, we scan the array of partial sums. And in the third step, we go again, read the whole input, observe that now we are not loading the per block scan, the array of per block scan. Here we are reading again the whole input array. We now perform the per block scan. At the same time, we send or propagate these offsets to the corresponding blocks, and then we perform the corresponding addition to obtain the final output array. So a good thing of this approach is that the add and scan the per block scan and the add operations can be executed inside the same kernel. And we will only have to read the input once and write it once. So in the end, we are saving memory accesses. So if you think about the reduce, about the number of global memory accesses in this reduce scan implementation in the first kernel that is reduced, we read the whole input array of n element, and we only have to write one element per block. So we have, which is the reduction result. So we are only writing this amount of elements that we can consider negligible. In the second kernel, scan kernel, we perform the scan of partial sums, but we consider the size of this array of partial sums negligible compared to the size of the whole input or output array. And finally, in the third kernel, again, a scan kernel. We are computing the per block scan, so we have to read the whole input array of n elements. After performing the per block scan, we add the offsets that we calculated in step 2, and we write the output of n elements. So in total, it's 3 n elements that are read or written to global memory instead of 4, as we had in the SSA implementation of scan, in the scan add version of the inclusive scan that we started discussing in this lecture. As you can imagine, in principle, we can expect that this RSS is faster, right? But still, that will depend on what's the size of the arrays and maybe other considerations as well. In GPUs, because we know that the access to global memory is the costlier operation, the operation with longest latency that we can execute on the GPU, we should expect this RSS outperform the SSA implementation. But as I said, this will depend on the size of the arrays. Why is that? Because if you think about the SSA, scan add, in the last kernel, we only need to add. And in addition, this is a very simple kernel. We just need to read all the elements of the input array and add one element to each of them and then write. There is no synchronization across the different threads that belong to the same thread block or something like that. However, in this reduction operation, as you may remember from the reduction lecture, there is synchronization needed. And here in this scan operation that is part of the third kernel in the RSS implementation, we also need to use synchronization primitives. We also need to use barriers, for example. And these are relatively costly, as you may remember, because we are somehow wasting execution cycles, right? So, yeah, so in the end, it's also, again, good to compare, good to try them. I don't have results that here in these slides that compare different implementations on GPU, but I can show you some results for another parallel machine, that is the AppMem processing in memory system, where instead of having SIMD cores, we have fine-grained multi-threaded cores, as you may remember, because I talked about this also in a previous lecture. In this fine-grained multi-threaded architecture, we have threads called tasklets that execute on the in-order cores that compose, you can see here, the DPU pipeline, the in-order cores that are these DPUs or DRAM processing units. And the tasklets, the threads that execute on this pipeline, can use handshakes to communicate pairs of tasklets. And these handshakes, you can see them in some way similar to the warp shuffle operation inside the GPU core, because they communicate different threads that are running on the same core. And also we can use barriers in this architecture as well, similar to the sync threads, to synchronize all tasklets. And we studied this architecture in a recent paper of us, and there we compare two versions of a scan. One is a scan SSA and the other one is a scan RSS. Here you can see in this figure that you can find in the paper, the execution time. Observe how for very small arrays, like for example, 2048 elements up to 8,192 elements, the SSA, which is the left, the column on the left for each array size, is lower than the column on the right that corresponds to RSS. And this is because the add kernel, the add stage in SSA doesn't need synchronization primitives that are relatively costly on this architecture. However, when the size of the array increases, at some point, the overhead of the synchronization primitives is not much anymore, and the RSS version starts outperforming the SSA version. So this is our reduced scan. We have compared it to the scan add version, and now we are going to see one last optimization and we will be done for today in order to see how we can, improve even more the performance of this scan operation. Remember that between stages, between phases or steps of this algorithm, we have to execute an interblock synchronization. We said that this is typically a kernel termination and relaunching and launching a new kernel. But another way is using atomic operations in global memory. And let me explain you how. In this reduce scan version, the first kernel calculates the reduction. As you remember, what we do is for each thread block, or in each thread block, one thread will write the reduction result into another array, and then we perform this scan operation. The way that we can perform this scan operation is by using one kernel, one new kernel on the GPU, or by scanning on the CPU, as we said before. But we can also do it using atomic operations, as we will see, because this is just kind of a sequential operation, right? And the only way, for example, to calculate this 20, the only thing that we need is this 6 and the result of the previous element, this 14. As soon as we have this 14 ready, we can calculate this 20. And as soon as we have this 20, we can calculate this 28. So in order to do so, what we can do is merging these 3 kernels into a single one and have threads using atomic operations, threads in each block using atomic operations to synchronize with threads in other blocks. And this is what we call the adjacent block synchronization. In the adjacent block synchronization, let's assume that we have this element, previous sum in shared memory that we declared before in the beginning of the kernel, for example. The adjacent block synchronization is executed only by a single thread block in the whole thread block. In this case, is thread block is a thread with thread ID equals 0, while the rest of threads are the rest of threads of the block are waiting in these sync threads, and we will have this thread 0 waiting for a flag. So observe that this while loop, the only thing that is doing is a busy waiting. We will have thread 0 reading some array of flags or one particular position in one array of flags by using this atomic add. Essentially is like simply reading in an atomic way, because we are adding 0, so we are not modifying it. But the thread 0 is all the time going to memory to read this element, and we do it in an atomic way in order to make sure that if someone updates this value, we are not reading a stale value, right? So this is the busy waiting. As I said, this flag resides in global memory, same as also this scan value array that we will access as soon as the thread ID, thread 0, leaves this while loop. When it leaves this while loop is because this flag's BID is not anymore equal 0. Now it's equal 1, whatever. It has been updated by another thread in a different block. And then thread 0 goes to global memory to a scan value, reads one value, writes it into this shared memory location, previous sum, and use it to perform, actually, to propagate the partial sum, to perform actually the calculation for the scan value. So here we are calculating the corresponding element for the scan of partial sums and store it in, again, a scan value in the corresponding position, the BID plus 1. Observe that this BID here in this code represents the block ID. So this whole, thread 0 that belongs to a certain block with an index BID is reading, is checking the flag that corresponds to its own block. When this flag is set, can go to global memory to read one value that has been written by someone else, someone else that the thread was waiting for, and then uses it to add it to the local sum, that is the local reduction that we compute in the first phase of the algorithm, obtain a new scan value and write it to global memory. For this operation to happen in a correct way, we need to include here a thread fence. The thread fence essentially is a consistent memory consistency point that essentially ensures that this write to a scan value VID +1 is completed when the thread 0 sets the next flag. So as you see, the thread 0 waits for some time until one thread from the previous block sets a flag. In that case, the scan value result is ready. We can update it and propagate. We use the thread fence to make sure that this scan value is already in memory, and then we set the flag and continue the execution. But now there is just one last problem here, is that this block ID cannot be the block index that we normally use. And why is that? Because we cannot assume any order in the scheduling of thread blocks. We cannot assume that thread block 1 is going to be scheduled after thread block 0 and thread block 2 is scheduled after thread block 1. That's not the way that the GPU schedules thread internally. So we cannot assume this linear scheduling, and that's the reason why we have to somehow generate a dynamic block ID. And as soon as a block starts the execution, we obtain this dynamic block ID with a simple code as this one, with a global counter in global memory that is accessed and updated by all thread blocks by one thread of each thread block at the very beginning of the kernel, obtaining simply a number, the result of updating the counter, and this number stored in this SVID in shared memory is going to be used as the block index in the execution of the adjacent block synchronization. The good thing of using this adjacent block synchronization is that we don't need to terminate the kernel after the first step, or we don't need to terminate the kernel until after the second step of the hierarchical implementation of scan. What that means is that we are reducing the total number of global memory accesses from 3n in RSS or 4n in SSA to 2n elements only. So again, we can expect, because the accesses to global memory are so costly on the GPU, we can expect that this will be faster than the previous implementations. And actually, I can show you some results in this case. Remember that these were we talk about scan applications in this slide, the fact that the scan is a basic building block in many parallel algorithms, and we experimented in the past with some of these algorithms, actually a group or a corpus of algorithms that we call the data sliding algorithms, because they move data in one direction inside memory. And examples of these are padding or unpadding. A padding operation, you all know what it means, is you have a matrix and decide to add an extra column, for example. Observe that row 0 doesn't change, but row 1 gets shifted one element or maybe two elements, depending on what's the number of columns that we are adding, but it's shifted in one direction, right? So it's shifted from lower address to higher address memory locations in memory. That will be a padding operation to include, to add an extra column at the end of a matrix, or a string compaction operation where we remove elements that we don't need anymore, right? And actually here I have one similar example, that is the select relational algebra operator. Imagine that you have an input array like this one, where we partition it into equally sized chunks assigned to different thread blocks from block 0 to block 2. And what we do here is removing those elements that fulfill this predicate, true if it's even. So we will remove 2, 0, 0, 4, and so on. And then we write to the output array. And if you see, block 0 will have to write 2 elements in the output array, block 1 will have to write 2 elements in the output array, and block 2 will have to only write 1 element to the output array. But in the end, the number of elements that each thread block writes depends on the values of the in the input array, right? And we don't know these values. We don't know the number of elements that each thread block will write to the output in advance. So what we do is calculating the exact offset, the exact index where each thread block needs to write. So block 0, because it's block 0, will write in start writing in element 0. But this block 1 needs to know how many elements is going to write block 0 in order to write to the correct place. So this 1 will go here, this 3 will go here. But to do so, we need to calculate these indices or the pointers to the place in the output where each of the thread blocks will write its own output, right? And the way to calculate these indices is by performing a prefix sum operation. So it's the reduction, the number of elements that this guy block 0 is going to raise 2, 2, 1. The prefix sum or the exclusive prefix sum is 0, 2, 3, right? And that's the way to calculate where to write in the output array. And here you can see a comparison of the select operation using prefix sum and using a prefix sum that employs the adjacent block synchronization. And you can see the blue bars are our implementation compared to the thrust library, and with a speed up that is more or less 3 times. This is an old version of both our own algorithms and also the thrust library. It's very likely that the thrust library is already using the adjacent block synchronization as well. So probably this distance got reduced, but yeah, you can try it by yourself in new architectures if you want, by downloading the code that is available in this repository. And this is all for today. I would recommend you read the corresponding chapter in the Programming Massively Parallel Processors book, chapter 8, which is about prefix sum. And yeah, that's all, as I said. Now I'm open to any questions that you may have. I don't see any questions in YouTube, but yeah, some people are watching. So thank you very much for attending. If you have any questions, feel free to use the chat. You guys in Zoom, please let me know if you have any questions. If not, I think we will be done for today. And hopefully we will continue next Thursday with one new parallel, important parallel pattern. Okay, seems that there are no questions. Thank you very much again for your attention. I hope that you enjoyed the lecture. I hope everything was clear. If not,